My name is Joachim Dengler, and I am a PhD of physics in the University of Heidelberg. Yeah, and after my exam, which means in Germany you have to be at home in physics, in the final exam they can ask you anything from any part of any field in physics. And so that's a good start for life. And I did my postdoc in information processing, mainly image analysis. I wrote the habilitation thesis, which habilitation in German means that this is the precondition if you want to become a professor one day. And it's about foundations of optimal model building. So this has also turned out to be quite relevant for the climate questions. And I had a great cooperation with the Harvard Medical School, with Ron Kikinis, and we were working on a brain matcher for intraoperative surveillance. And after that, I had a company of my own and I had 2 patents in fingerprint analysis, working together with Scotland Yard and also a bit with the FBI. And after that, I went into IT consulting, and only over the last 5 years, I got into the climate research. But in that time, I have already 2 peer-reviewed papers, mainly on the relation between emissions and concentrations. And I have a blog called klima-fakten with a k.net. And it's partly in German, but most of it also is translated to English. So now let's dive into it. I want to speak about the climate narrative and how does it relate to science. I always thought in the last time, how can it be that this climate narrative is so universal? I mean, it's in so many universities, and really clever people are aligned with it. And it cannot be that it is just all a bunch of lies or only propaganda. And the conclusion I have come to, and this is what I want to discuss also tonight, the climate narrative always begins with a correct observation or a correct law of physics. And now let me tell me something about the coloring. Where it's in black, that's about science. And where I want to question things, that I mark with red, yeah? And then after the correct observation or the law of physics, there are various ways you can twist it, yeah? It may be that a certain observation is correct for a certain amount of time. We will see for 30 years, for example. And if you just extrapolate this over 50 or 100 years, it becomes wrong. The other way is you start with a correct law and then you exaggerate or twist it. And the great recipe, if you do these things, you put your results into the future where they are really hard to verify, and it's very hard to oppose such a statement which comes from apparently correct science, which makes terrible prognosis for the future, but you cannot get a grip on it. Yeah, it's very hard. And also there is a subjective point. We are all humans, yeah, and we have our doubts, we have our feelings, and a glass can be half empty or half full, yeah, and in the way how you look at it. And what I find in the climate narrative, when in doubt, always point into the direction towards maximum catastrophe. So what we want to do here is ask, what does science say? And in this presentation, I want to really to stay very conservative, what I would call the non-controversial accepted science. Yeah, I have listened to some of your podcasts where people have really very interesting, revolutionary ideas, which are very worth discussing and very valuable. But I will refrain from all those today. I want to stay with what you could call mainstream science. I will make a few excursions one here or there, but mostly I will stay with the non-controversial. And then to some people in this community who say, "Wow, you are following the mainstream. What are you doing?" And to those, I want to say, before you judge someone, you need to walk a mile in their shoes. You need to go with them. And in particular, in one field where also my research was, it was very, very helpful to really understand and long talk to a representative of the other side, and to at least understand what is their point they want to make. Yeah, and if you understand the point, then it's easier to discuss, and also it may be more fruitful. Now let's turn to the 4 points I want to make. We look at the science, and we look at the climate narrative elements. Yeah, we can imagine this to be the 4 legs of a chair. Yeah, if you get one leg breaking, then this chair becomes shaky. Yeah, but if you break 2 legs of it, then the whole thing collapses. That's the idea. And I could nearly say you can freely choose which legs you want to crack, and I'll offer you 4 of them today. Now, the first one is anthropogenic emissions are rising, and typically they're rising exponentially. That's what we have been hearing. People have been saying that, and sometimes even today. And if you think of the RPC 8.5 scenario, that's exactly what it is all about too. That emissions keep rising exponentially until all carbon is burnt. Yeah. Okay. Here on the left we have the emission curve, and you could say, okay, here has been some exponential growth, then there is a dip, and then another exponential growth, but we don't know exactly what happened here. But if we analyze this and look at the actual emission growth, then we see that indeed, after 1945, at the end of the Second World War, we have the start of a 30-year period of exponential emission growth. It has been true for 30 years. Yeah, it was a growth of 4.5%. As a matter of fact, when we have a bank account and we get 4.5% interest, we don't worry too much that it is exponential growth. Yeah, but and also this phase in history, at least in Germany, this phase was actually positively connotated. We called it the economic miracle. Yeah, but it was accompanied by a 4.5% emission growth. And now could say the historic tragedy happened that in the 60s and in the 70s, climate research began, yeah? And researchers didn't know anything else but this exponential emission growth, yeah? And so in early climate models, at least, exponential growth was actually built into the models, yeah? So that there was no question about the way it would continue. But the fact is that there was a reduction in 3 waves, yeah? There was a reduction down to 0 emission growth, 1980. We called that a recession. And if you look what happened, effectively this caused a government change in the United States and in Germany. Yeah? In both countries, the people were not satisfied with their governments anymore, so they changed them. And it was not only the personality of the president or the chancellor, but you can see it objectively. The emissions went down to 0, yeah? Emission growth. I mean, the emissions itself didn't go down to 0, yeah? But we had this dip here, yeah? And then it went up again. We called it economy is recovering. And then in 1990, there was again nearly down to 0. That was the collapse of communism. Yeah? And then again, it went up. And since 2003, we have what you could call planned reduction in emissions. Yeah, that's where the environmental movement comes in. Yeah? And meanwhile, also according to this curve, we have reached 0 emission growth. But the climate models still pretend growing future emissions. And now let's look at in more detail. Fact is, and this has been published by Silke Hausfather, who can by any means of the imagination not be called a climate denier. Yeah, he has done serious research and he found out actually human anthropogenic emissions have been flat since 2011. Yeah. There has not been any more global emission growth since 2011. I think that's remarkable, and I wonder why this is not published anywhere. This is not controversial knowledge. Yeah, I mean, this is very public knowledge. Okay, I did a bit of research on this and looked at it in about more details. Now, this blue curve is not emissions, but this is concentration growth in the atmosphere. If you take the Mauna Loa curve, and if you do differentiation, if you do the differences from one year to the other, yeah, then you can measure the growth in emissions, yeah. And you can see emission growth is very noisy, yeah. And the reason for the noise are in fact the natural emissions, which very much correspond to changes of temperature. Yeah? I mean, Roy Spencer found that out, and I could confirm it in my research also. And if you know this, you can make a model of the emission growth, which is much more flat and not noisy anymore, but it reflects the kind of true emission growth. And if you follow the true emission growth, you see the maximum emission growth of 2.5 ppm per year has been already in 2013. Yeah? The absolute maximum of emission growth was in 2016, but that was an El Nino year. So this is strongly modulated with the heat-induced natural emissions. Yeah. But no matter, you can also take the 2016. That makes not much difference whether the maximum is here or there. It's it's not much difference. The main message remains. There has never been a higher emission afterwards. And you can see if you start here, it goes steeply down. If you take the average, there is a slight decay, but it continuously goes down. Yeah, the rate of increase in yearly emissions. Yeah, and this corresponds very nicely. This is what you expect if you have constant emissions. We will see that a bit later, why this is like that. Okay, the first conclusion is the horror emission scenarios are completely irrelevant. The two IPCC scenarios with still growing emissions, RCP, or if I mix that up, could be 8.5, avoid at all cost, it's called, or the 6.2, which is dangerous, are irrelevant for evaluating the future. That's all unscientific fear-mongering if you use these scenarios. And in fact, the goal number 1 of the Paris Climate Agreement has been reached. Countries should reach maximum emissions as soon as possible. Yeah? And even the International Energy Agency admits peak emissions are likely to be reached in 2023. Okay, there was a band called 10 Years. But there is a general agreement among the experts that peak emissions have been reached already. Yeah. It's a matter of the past and not of the future. And so, even if you believe the whole rest of the climate narrative, these easy-to-check facts give strong reason to change the whole discussion. The worst case in the future are constant emissions of 37 gigatons of CO2 per year. So this is a front where Professor Roger Pielke is fighting a good and strong fight, and he's, even with such facts, they call him a climate denier. Yeah, but this is something which can very, very easily be checked there, that you don't need much science for that one. Okay, let's come to the second leg of the chair, which says atmospheric concentration is continually rising if emissions are not reduced to zero. So the fundamental question is, how is atmospheric concentration related to the CO2 emissions? It is known that not all CO2 remains in the atmosphere. We probably all know this picture where we have the fossil fuel emissions, the land use change, and then we have the big sink systems, which are the oceans in the dark green, which are the land plants in the light green, and only the rest, which is light blue, goes into the atmosphere. But here, when we look at this picture, the twist of science already starts. Yeah? Intuitively, we relate the natural sink effects to emissions. And people say approximately half the emissions are absorbed. Yeah, and while this is literally true, from a scientific point of view, it is very questionable. Now let's look at it a bit more detail. We have emissions versus concentration growth. Yeah, and here we see the important observations. Not all emissions, which are blue, contribute to the concentration growth, which is orange. Their difference is the sink effect, which is green. this is absorbed by oceans and plants. But these things are not only absorbing anthropogenic emissions. How can they know what are anthropogenic emissions? It's the same CO2, yeah, anthropogenic or the natural CO2. It's always the same. The carbon circle is a complicated system of natural emission, natural absorptions, and anthropogenic emissions. And the $100,000 question is how much remains in the atmosphere. Yeah, and people having accepted this diagram where half of the emissions are absorbed, the other half remains in the air, and that's what they call the airborne fraction. Yeah, and in the early days, they considered a constant airborne fraction of 50% or 60% CO2 as a kind of scientific law. And obviously, when always half of the CO2 remains in the atmosphere, the concentration will rise and rise and rise, and you cannot stop the rising if you don't reduce emissions to absolute zero. Yeah. But if you look carefully, the assumption of constant airborne fraction only holds for exponential emission growth. Otherwise, it does not hold. And you can see in the diagram, while from 1960 to 1990, it was approximately constant. It's very noisy, the curve, yeah. But if you smooth it a bit, you see that it's approximately constant. After 1990, there is a large dip. But overall, if you look at the whole 60 years, you see it's continuously going down, this ratio. And if we had a so-called net zero situation where you have emissions and absorptions were equal, then it would go down to zero. So the concept of airborne fraction obscures physical and biological laws. Now, the next scientific approach was the famous Bern model. There were Swiss physicists who, in the 70s, were building a carbon cycle model. Yeah, and the basic idea is correct. The carbon boxes are finite because carbon has no way to escape forever, yeah, because carbon from the atmosphere can go into the land plants, it can go into the mixed layer of the ocean, and from there into the deep ocean, and possibly back again, yeah. And then from certain observations which had to do with the so-called bomb tests, they arrived at the so-called Bern box diffusion models. 20% of all emissions will remain in the atmosphere for at least 1,000 years. And intuitively, it's very hard to swallow, yeah? And only after a few hours of discussion with one of their representatives, Professor Hyman, whom I met recently, we had very interesting discussions. I finally understood how do the 20% come about? Because they say the diffusion into the deep ocean is so slow that effectively only a volume which is about 4 times the size of the atmosphere is effectively used in the ocean for absorbing CO2. So if you have 2 boxes, one with 20% and the other with 80%, so obviously if you distribute the CO2 among the two, you end up that one takes up 80% and the other keeps the 20%. Yeah, but effectively the ocean, but it's not 4 times larger, but it's at least 50 times larger. Yeah, and only when you assume this very, very slow diffusion into the deep ocean, and only then you can get a behavior which is reflected in this burn model. And the important thing is that the burn model is in the core of the global climate models. Yeah, burn model or a similar model of that. And yeah, and a lot can be said, but let me restrict myself to just one important argument. The burn model transport process is much too slow because it ignores the marine biota. The marine biota, they transport carbon into the deep ocean by gravitation, because the dead plants, they just fall down to the ocean, to the bottom of the ocean. So the transport is by gravitation and not only by diffusion. So this is a hard one. That's a very subtle one, and the discussion is not finished. It will go on, but this is what we've currently found out about it here. Now, contrary to this is a model which other people, but I also have worked upon. When we relate emissions, when we relate the concentration growth, not to emissions, but to concentration, then we get 0% remaining in the atmosphere. The natural sinks are related to concentration, not to emissions. So if we take the diagram again, if we have the sink effect, and the red line is the 2% line of the atmospheric concentration. So 2% of atmospheric concentration is absorbed every year, and that compensates all natural emissions and the current 50% of anthropogenic emissions. When concentration grows, more emissions are compensated. And this explains why we have falling concentration growth with constant emission. Yeah, because concentration grows, so the sinks are growing, but emissions is staying constant, and therefore concentration growth has to go down. And we can calculate very easily with current anthropogenic emissions. The net zero equilibrium is reached when CO2 concentration is 520 ppm. It cannot grow further than 520 ppm when this linearity relation continues to hold. And this is where the interesting discussions come. But over the last 70 years, there is not the slightest deviation from the linearity in this relation. You cannot see any systematic deviation. So we are confident that it will also hold for the next 50 years, and that's when we will have reached the net zero. So constant emissions are not even the most likely scenario. According to the International Energy Agency, that's the projection of the current implemented policies. They call it stated policies. That means constant emissions until 2040, and then a slight decrease of 0.3% per year, kind of hardly noticeable. Yeah. And under these conditions, concentration will peak at 475 ppm in 2080. And here is a nice calculation, easily to remember. Before 2020, we had 130 ppm concentration growth since the beginning of industrialization. After 2020, we will have 65 ppm concentration growth, which is just half of that. So that is the scenario, and the conclusions with the current policies. The goal 2 of the Paris Climate Agreement, the equilibrium between emissions and absorptions, will be automatically fulfilled. There is no need for zero emissions. The future CO2 concentration will stay under 500 in ppm, and if we accept that CO2 fully controls temperature, which some of us may doubt, the 130 ppm rise caused 1 degree of warming until 2020. And logically, we can expect from another 65 ppm, we can expect another half degree of warming. Very simple calculations. Some people don't like this kind of sensitivity computations, but where you are, that I think it's easy to understand and easy to follow. This means that from a CO2 point of view, also the 1.5 degree goal of the Paris Agreement will be automatically fulfilled before 2100. So even if we believe in the whole CO2 stuff, there is no need for worrying. Okay, let's come to the third point. Now we come to the CO2 concentration growth, and which apparently causes dramatic rise of temperature. Okay, as I said, I will restrict myself to a long-established physical scheme or method. It's called radiative transfer. This is well established in physics. And according to radiative transfer, we have a reduced flow of energy to space when we add CO2. And now why am I fairly convinced about the validity of radiative transfer? And we may have some discussions with people who are not convinced about it. May be interesting. This diagram, you can see we measure the outgoing long-wave radiation with a satellite in the black curve. And we simulate that behavior with the MOTRAN program, which models the radiative transfer. And the nice thing about MOTRAN is it's a public program which everybody can use. So you can simulate pretty much the exact infrared behavior of the spectrum with MOTRAN. And honestly, this gives me quite a bit of confidence that it is not completely wrong. I mean, there may be things which are questionable, but it's not bad for a start. And now but it helps a lot to understand how IPC thinking works. Now, IPCC uses a very, very special planet. The planet has the following. The atmosphere consists only of CO2. There's no oxygen, there is no nitrogen, no, there is oxygen and nitrogen, but there is no water vapor. And we have full solar insolation, and there is no albedo. Yeah, so we have the 280 ppm, pre-industrial, and we get the 340 watt per square meter. And now what we do, we are doubling CO2 to 560 ppm. And what do we get? We get minus 3.77 watt per square meter. And this number, this you find in all the IPCC publications. This is called the greenhouse effect here. And what you find less in the publication, that even if you take this number and you start to heat the Earth, you can do that with Watran. You can, if you heat it with 0.8 degrees, then you can balance this out. So you can say about one fourth, bit less than 1/4 of that number is the actual temperature increase of the greenhouse effect. But this is an absolutely unrealistic scenario. This has nothing to do with the real Earth. So let's gradually start becoming more realistic. The first thing we need to do, even if we have no clouds and no water vapor, at least we have Earth albedo. Yeah, the Earth's surface is reflecting light and pushing it back into the space. So if we take approximately the same number as on the moon, which is not a bad start, because water has also about the same albedo as the 0.25. Then the insolation is not 340 watts per square meter, but 297.5. And now here is the only scenario where we do not double CO2, but we have it from 0 to 280. With 0 CO2, we get a temperature of -2, not -18, as most people say. Yeah, if you calculate, you get a temperature of -2 if you consider the Earth albedo and no cloud albedo. And then if you lift the CO2 to the pre-industrial level of 280 ppm, you get a real large forcing of 27 watts per square meter. And this is compensated by 7 degrees. So that's normal greenhouse effect of CO2. Yeah, that's for the sake of just being there. Yeah, it's that CO2 keeps the atmosphere warm. Yeah, and so the average temperature is then 5 degrees. Yeah, when we increase from -2 to 7 degrees, then you reach 2. And now we have again, only CO2 in the atmosphere. We have no clouds, no water vapor, but normal albedo. Yeah, and so under these conditions, you only have 270 watts per square meter coming in because of the CO2 content. And the temperature, so-called pre-industrial temperature, is 5 degrees. And then if you double this, your forcing goes down to -3.2, which is compensated by 0.7 degrees. Okay, now these are all unrealistic scenarios, yeah, because there is water vapor, there are clouds. So if we have the normal so-called standard atmosphere, the pre-industrial standard atmosphere, where we have an albedo effect altogether of 0.3, so 30% of the light is reflected into space, and the solar insolation is on the well-accepted value of 240 watts per square meter. We have the CO2 before doubling, and the temperature is 15 degrees, as well established. And then we double the CO2. The forcing is not minus 3.77, but only minus 2 watts. And this is compensated by half a degree of warming. So the sensitivity, the CO2 sensitivity, is not 0.8, but 0.5 degrees, half a degree. And for curiosity, we can ask, how much was the effect until today? We again start with pre-industrial conditions, and CO2 after the doubling, not doubling, but we have 420 ppm right now. The forcing is only 1.1 watts, and that corresponds to 0.3 degrees. So we can say that it is scientifically solid to assume that since pre-industrial times, the atmosphere has warmed by 0.3 degrees due to CO2. Yeah, that I can accept, and I can scientifically live with that, and also it's very hard to disprove. Okay, so we need to correct the mainstream sensitivity narrative. Sensitivity measurements have to be done with realistic conditions. First, we need to consider albedo. 30% of solar installations are reflected back directly to space. They are not relevant for warming. Therefore, the greenhouse effect is reduced from 3.7 watts per square meter, the forcing, to 2 watts per square meter. This corresponds to 0.52 degrees warming. The real values are approximately half the values that are reported by IPCC. During the last 40 years, with very large CO2 increases, there were 0.14 watts per square meter per decade as measured per Motran. And in mainstream literature, it is 0.2 watt per square meter per decade. Yeah, so the 0.2 watts is already mainstream, and 0.14 is what I get from the Motran emulation. So if we agree to a rise of 0.7 plus minus 0.3 watts per square meter, it should be a very diplomatic solution. So, and we can, the final statement, the 0.3 degrees temperature rise caused by CO2 since the beginning of industrialization. So that's realistic. But then we come to the fourth point, yeah, and that's where the music plays, the positive feedbacks, yeah. And there are even tipping points of no return, the leading to catastrophic consequences and all the rest of it. We know that from just listen to any news in the world every day. So let's put things together. The physically justifiable greenhouse effect, even if it's exaggerated, is 0.8 degrees sensitivity for doubling CO2. Okay, we found it's 0.5. Yeah, and so it was recognized very early that this would not worry anyone. So James Hansen who wrote a paper in 1984, and in order, because with 0.8 degrees centigrade, he wouldn't have been able to create panic in Congress. which he did later on. But he said he must introduce something which he called feedback. And if you read the paper of James Hansen, 84, he said the main feedback which is applied is the so-called water vapor feedback. And so he introduced the feedbacks, and in the course of the time, sensitivity could be arbitrarily magnified, for example, to the 3 degrees for doubling, which is currently propagated. Some people even propagate 5 degrees or 7 degrees. So I want to restrict myself to have a closer look at the water vapor feedback today. Now, how does the water vapor feedback work? The water vapor feedback is a 2-step process. When air temperature increases by 1 degree, it can take up 6% more water vapor. In the literature, you will usually find 7%, but if you look more closely, the 7% only apply at Mount Everest in 8 kilometers elevation. Yeah, but so I rather stick to the 6%. Yeah, but the calculation doesn't change much if we take 7%. So the air can take up 6% more water vapor, but it does not have to take up. Yeah. So if you are in the desert and it gets hot, if there is no water on the ground, there is no water vapor in the air. Yeah. So it's as easy as that. Only all this applies more or less only about on top of moist areas or on top of the ocean. Now, on the other hand, infrared radiative transfer on transport depends on relative moisture in the air. Additional moisture reduces outgoing infrared due to absorption of water vapor. So these are the 2 steps in the process. And the question is, how large is the total feedback? Again, we use our Modtran program, and we do that the following way. We start with a standard atmosphere. By the way, standard atmosphere is a technical term. It is an atmosphere with certain features, and this atmosphere has been used for aviation for at least 50 years. Yeah, so all the aeroplanes which are flying essentially depend on calculations with the standard atmosphere, obviously modulated by local weather events. Yeah, that's clear. But essentially, all the calculations, for example, with about the density of the air and the humidity and all these things, they usually use the standard atmosphere, and it has been working very, very well. Yeah, it's a very proven standard. Yeah, and it's approximately the average atmosphere. So let's use the standard atmosphere, adjust to 80% relative moisture, which is about in the middle of the scale. And then again, we need to adjust the clouds to come close to the real 240 watts per square meter total radiation. This is the setting. And then we add 6% to the relative moisture. And we see infrared radiation goes down 0.7 watts per square meter. And then we increase again the ground temperature to balance the radiation. And we have to increase the ground temperature by 0.19 degree for a 6% humidity rise. Yeah, so a 6% humidity rise causes a greenhouse effect of 0.19 degrees centigrade. So we take this together. When 1 degree warming causes 0.19 degree additional warming, this works recursively because the 1.19 degree again have a feedback. Yeah, so it's an infinite series, and this is a so-called infinite geometric series, and which adds up to a total feedback of 1 over 1 minus 0.19, which is 1.23. So the feedback factor is 1.23, 1.25. Yeah. So when we use, in fact, James Hansen's greenhouse effect, which he wrote 0.8 degrees feedback, 0.8 degrees centigrade, with feedback that would be just about 1 degree centigrade. When our basic greenhouse effect up to now is 0.3 degree with feedback, it would be 0.37 degrees. So the total greenhouse effect with feedback since the beginning of industrialization has been less than half a degree. Okay, but usually when I talk about this, the first question in the discussion is, but there has been warming. Haven't you noticed that since 1900? Okay, I remember or remind of St. Augustine. Look what you are looking for, but not where you are looking for it. This applies not only for happiness, as Augustine wrote about, but also for climate issues. Okay, let's make a test in Germany. Yeah, that's for me the easiest one to test. The German Weather Service, fortunately, not only gives the temperature data, but they also give the sunshine duration data. And if we look at the sunshine duration since 1950, or I think it's 1951 to 2023. Yeah, so it's quite rather complete. Then we have in fact a 1.5 degree increase in 10 years. This is a lot. 1.5 degrees in 10 years is quite a lot. So we in the 70 years, from where the average is 1,500 hours per year, the increase is 168 hours. That's more than 10% in the 70 years. That's really a lot. And so I made, after having seen that, and I thought I make an experiment. Yeah, I thought I give both the sun and CO2 a fair chance to explain the temperature increase or the temperature over the last 60 years or 65 years. Yeah. And so I did a regression test, but that you have to take monthly data for this to work. Yeah. And what I found out, there is no measurable greenhouse effect in Germany. So I don't know how it is for the rest of the world. But in Germany, I can prove that CO2 influence is below the significance threshold. And 90% of the temperature variability can be explained by latitude-weighted sun hours. It was quite an experience. I have no worldwide data for this, but it may be an interesting field of research to look into. But what can be done to do worldwide extrapolation for this. Other people have investigated the reduction of the worldwide cloud cover over the last 30 years. And I have quoted the paper, and I have also a literature list in the last page. From the reduction of cloud cover on a worldwide basis, we have 0.08 watts per square meters in 10 years. And if you remember, the CO2 forcing in the literature was 0.2 watts per square meters in 10 years. So from this basic calculation, we can say that at least 80% of the warming has been caused by clouds, and at most 20% has been caused by CO2. I mean, I must say the 80%, that's measured data, and the CO2, 20%, that's postulated. Yeah, that's from the theory. Okay, here are my sources, and so that's my conclusion. Yeah, that most of the effect is from reduction of sun cloud cover, but listening to your podcast for you, that's not something new. But I thought I tried to walk as long as possible in the shoes of the others to finally come to the same conclusion as others in your podcast have also come.
Do you have any idea of what is causing the fluctuations in clouds and when it might reverse and we might see more clouds or increasing cloud?
It's a great question. I mean, Tom Clauser would give you some good answers on that one, I suppose. But well, it's a funny thing that clouds are very, very hard to analyze. Yeah, because you see, if you do the very naive thinking would be, I mean, we know that the temperature has been increasing over the last 50 years, then you would normally expect, with more moisture in the air, you would also expect more cloud cover. Yeah, that would be the intuitive thing. But fact is, this is not the case. Yeah. But now there are other factors. Yeah, I mean, one factor, you see, I am born in an area of Germany. I was born in an area of Germany in a city called Duisburg, yeah, which is in the Rhine-Ruhr area, yeah. And when I was born, my grandfather, he was a coal miner, yeah. And at that time, this was the dirtiest place in Germany, yeah. You could not go out. You didn't see any sun there, yeah. And obviously there was a lot of steel production, ThyssenKrupp, yeah, and a lot of coal burning. And so lots of aerosols. And one thing I think we all know now, clouds need seeds, aerosol seeds, yeah, to be created. So there was more from that point of view. And you see, people were burning wood and were burning coal in winter. Yeah, I mean, you see, when I was an exchange student in England when I was 15, yeah, I was living with a family in Mansfield. It's also a coal area, and the father of the family, he was working in a company called Rexco, and they were proud to produce smokeless coal. That was the thing, and London was really messy at the time. Yeah, and that was 68. Yeah, that's not so long ago. So in all our also industrial countries, we had lot of smoke in the air, lot of smoke. We have steam engines, yeah? And so there were lots and lots of aerosols. And then in the 70s and 80s, you see, our cars start to have catalysts. Yeah, the sulfur was taken out of the smoke from cars. Yeah? And sulfur dioxide is a very strong aerosol. So and then there was an experiment, an involuntary experiment. On 9/11, you had 3 days of no aeroplanes in the United States. And you may remember, it was the clearest days over a long period. There was no cloud in the sky. Yeah, and then obviously the recent rise in temperature. I mean, people have been talking a lot about that, and even mainstream people say that this is so sharp it could not have come from CO2. Yeah. And so some papers have kind of localized and attributed the most recent temperature rise to the cleaning, to the filters in the container ships, yeah, which do not throw out all the dirt which have been doing in the past. Yeah. So these are just hints. I could say this is not a scientific study. Yeah? These are hints, and only the appeal to do more studies in this direction. Yeah, that's all I can say. Yeah.
Okay. I do have one more separate question here. I'm going to put a link to a YouTube video in the show description. It's by Tom Segalstead in 2009. And he's arguing there, the quote, that the oceans take our anthropogenic CO2 gas out quickly by dissolving it as bicarbonate, HCO3 minus,
Yes.
which in turn forms solid calcium carbonate, either organically in calcareous organisms or precipitates inorganically. Do you think that is the thing that's happening? Maybe that it's just precipitating out of the ocean and falling to the bottom of the ocean?
Well, this, you are touching the very, very hard and difficult discussions which we had also with Professor Heimann from the Bern team, yeah, because you see the Bern team, their main argument is that the diffusion process into the deep ocean is very, very slow, yeah, and it is very difficult to have evidence, yeah. But the trouble is, you see, there are more arguments which could be said, yeah. What is missing also in the discussion, except the marine biota, yeah, which is a very, very strong factor, yeah. There, I think, 12 gigatons of carbon are going down by gravity each year, yeah, which is the dying marine biota, yeah, and the calculation goes about like that. You have 3 gigatons per generation, and there are 4 generations per year, yeah. And also, what is also missing in the mainstream discussion, you see, the Bern model is a diffusion model, and diffusion is about the slowest process you can think of. Yeah, if you have only nearest neighbor interactions, it's a terribly small process. Yeah, but what you have are ocean currents. Yeah, you have the Gulf Stream, which goes across the Atlantic and goes down at the pole. Yeah, you see, these ocean currents, they need to be evaluated, and the trouble is, these are difficult computations. These are difficult. You cannot do it with easy computations. Yeah? So sometimes the science appears to me like the drunk guy under the lantern. Yeah, and the policeman comes. What are you doing here? Yeah, I'm looking for my key. Yeah, I've lost my key. Yeah, where have you lost it here, or where do you have lost it? Yeah, over there. But over there it's dark. Yeah. So that's sometimes what I'm afraid that we are not facing the difficult questions. Yeah, and the difficult questions are the ocean current. My co-author John Reed, he has been working a lot on ocean currents, and he has also written a book about it, about the what is called some kind of catastrophe, but he always said the ocean currents are the missing factor, and because the trouble is these are not continuous circulations, but these are I'm now missing the English word, wirbel. Yeah, these are turbulence. These are turbulent. These are turbulent currents, and you have not a good mathematics for turbulent currents. Yeah, that's the problem. Yeah, and so people tend to evade these difficult questions. Yeah, and it's difficult to prove anything along these lines. It's difficult to disprove anything, but everybody knows these are there, but people are not taking it up. Yeah, the same thing with clouds. Yeah, there are so many factors connected with clouds. Yeah, you know there is Svenssmark's theory and Chavif's with the interaction with cosmic rays. Yeah, and there are really weird things happening with clouds. Yeah, there. If I make a statement about the low-hanging clouds, then I'm sure somebody will come up with the cirrus clouds, which has only a greenhouse effect and no reflection of the sun, and it's a hard one. Yeah, and I'm trying, and I'm really looking forward for a real good scientific paper from John Clauser, yeah, where he tackles this, and I mean, he should be able to formulate that. I mean, he has a Nobel Prize. That's also a commitment to produce something really sound. Yeah, that's my challenge to him.
Excellent stuff. Any other points you want to make before we finish up here?
Yeah, to all the people who say it's the rise doesn't come from anthropogenic emissions, I want to say that's also a good news. You see, the biological things, yeah, biology is a strict thing. There is, you see, people say, but there are so many natural emissions that human emissions are drowned by them. Yeah, you must have heard this argument often. Yeah, and to those I say, if you take biology, yeah, and if you analyze it clearly, yeah, if before I say biological emissions are a contributing factor to the concentration growth, I must think, you see, every atom that I breathe out or my cow breathes out, yeah, by the carbon cycle must have been extracted from the atmosphere before. Yeah, if I eat a piece of bread, that grain has been grown 2 years ago because it has been stored somewhere, yeah, and it takes time before it becomes bread, yeah. So it's all, everything in biology comes from the air. Already Richard Feynman said that, yeah. So biology, by definition, is a carbon sink. It cannot contribute to emission growth by definition, yeah. And the oceans are, you can imagine, as carbon stores, yeah, with long storage times, centuries of storage times, yeah. But so currently we store the low level of CO2, which has been prevalent over the last 500,000 years, yeah. You can see that from the ice core data, yeah. So the average of 250 ppm we had in that time, yeah. And so oceans are stores, yes. And now we have a higher concentration, and that means because oceans have lower, they are acting as sinks, yeah. And if our concentration, God forbid, would go lower than 200 ppm, oceans would act as sources again, yeah. And so, and unless we have catastrophes, of course, if whole, if all Australia, or all the United States, if all the forests or all Russian forests would burn, yeah, by a huge catastrophe, by a impact or something like that, then obviously we would get an carbon source there, yeah. Obviously, everything would burn immediately. But as long as nature is approximately in balance, yeah, and the little forest burn which we have is negligible in this context. Yeah. As long as we have this, we are rather balanced. Yeah, you see, the only really big exception which we had in the last 50 years in this carbon balance, in this, was after 1990. There was the Pinatubo eruption. And that's also a strange thing. Most people think that Pinatubo or volcanoes would produce carbon dioxide, yeah. But after Pinatubo, we have an extremely deep carbon sink. There was so much carbon uptake of nature as never before in our measuring interval, yeah. And so, and Roy Spencer has a very interesting theory for this. He said Pinatubo created, by these particles which were sent up into the atmosphere, created a strange kind of diffusive light, yeah. So there was less direct insolation, but more indirect insolation. And that increases photosynthesis enormously if you have indirect insolation. And when I told this story in a recent meeting I had with interesting people, then one of them, who has been in photovoltaics, and he said exactly the same thing happens in photovoltaics. When you have a little bit of dizziness, the PV modules produce over the day more electricity than if you had 100% direct insolation, yeah? Because you also get the light which comes from the non-optimal directions, yeah. And so this may be a concluding remark. There are many interesting phenomena.
I don't recall ever hearing that. Very interesting. So I'll let you go now, but thank you very much. This is great stuff. We'll have to do it again.
Okay. Thank you very much for the invitation. Good luck to you.
You too. Goodbye.
Bye-bye.